This paper demonstrates that rich regularization naturally arises in many data science problems. So this paper is called Rich Regularization, an Essential Concept in Data Science by Trevor, Hastie, Statistics Department in Stanford University, January 23rd, 2020. From this paper, you will get several examples of where rich regularization arises, and hopefully you will get more insight and will be able to use it in other cases or understand better. Rich regression, sometimes called L2 regularization. So in case of a linear regression, rich regularization appears in the same to solve a problem of poor conditioning with a matrix that appears there. So when you are solving least squares regression equation, you need to do inversion of data matrix transpose times data matrix. But this matrix can be poorly conditioned. For example, it can have 0 singular values, or can have very closely 0 singular values. So there could be, problem inverting it. You can solve this by adding to this matrix a diagonal matrix of lambda times unit matrix, and you usually can do inversion after that if the lambda is sufficiently large. And actually, if you do that, you'll find out that this is the same as doing least square minimization, looking for a solution of linear regression, where we add this extra term of rich regression, or L2 regularization, rich regularization. So that is plus lambda of the solution L2 squared. This can be also, you can get more insight into this by looking at SVD decomposition. So if we take this matrix of X transpose times X, and we do SVD of the matrix X, we will actually find out that adding this extra plus lambda unit matrix will actually add to the diagonal a lambda, which effectively will pull to 0 contributions from vectors which have which are singular values, which correspond to the singular values. It will also make correlated variables shrunk towards each other. Their contributions, because you will effectively be getting rid of the contributions from that space that is that have very small singular values. So as they say here, with lambda bigger than 0, the coordinates of the solution are shrunk by an increasing amount as we go through the section of the principal components. They have one section on rich and bias variance trade-off, but I will skip that. I will go to the rich and data augmentation section. So there's interesting insight here that if you take the original data and around each data point you generate additional samples with same labels, but and you do that by using perturbing original data values with adding this error term of normally distributed closer around the original data points. And if you do that, this will be approximately using as if you were using rich regularization. So that's quite interesting insight. at least in case of a linear regression. Rich and dropout regularization. So dropout is basically turning off some of the activation inputs and correspondingly inflating others. And the other inputs need to produce the same output, effectively standing in for the omitted input values. And if you look closer at this, in case of if we do this for least squares linear, again this will be equivalent to ridge regularization. They have a section on ridge and lead one out, ridge and kernel trick, but I'm skipping that. Ridge minimum norm and double descent. I'm going directly to the conclusion. So I'm citing, we see through these examples that ridge regularization and its extensions are pervasive in applied statistics. Although the lasso enjoys widespread popularity in wide data, for example genomics, both ridge and ElasticNet claim some of the territory. So thank you very much. This was a quick spice and juice of the paper of ridge regularization, an essential concept in data science by Trevor Hastie, 2020. Please unsubscribe and dislike this video, and I hope to see you next time. Bye bye.